Worksheet 3. Let me look for that real quick. I gotta get the music off the screen here. So let me do this. I have to open that from here. Uh, 140 worksheets, unit 3. Oh, for a second I thought I was missing like 2 worksheets. I renumbered them. Unit 3, okay. So, question 1P. Now I can't see the screen, so I gotta do this. Window capture that. Why is this so wide? Like, that's not gonna help anybody. Oh, you know what I can do. I can then go to this and just scroll it down. I can't actually see it on my screen, so I'm just trying to... There we go. Okay. So a question was asked, how do I do this conversion for problem P here? So these are accelerations. Not that that's relevant to solving the problem. That's just, in case you were curious. Kilogram meter per second squared is a... Oh, no, wait, these are forces. Sorry. I was like, wait a second. Accelerations don't have mass in them. All right, so, oh, I gotta zoom this in. This is too big. I don't want that on my screen. All right, so we have 1,800 kilogram meters per second squared. And I want to get kilogram meters into pound miles per minute squared. Now, the way that you would do this is you would do a dimensional analysis conversion to just change each unit into something else. So you could do kilograms to pounds directly. You could do meters to kilometers to miles. And you could do seconds to minutes, but you'd have to remember you gotta square it. So I should have 1, 2, 3, 4 conversions to do this. So let's do those in order. We'll do 1, 2, 3, 4. I'll circle these to indicate what steps we're doing them in. So my first conversion would be to get kilograms to pounds. So I don't want kilograms, so we're going to cancel it. Oh, the chat might be frozen. Sorry if I hide the chat. It was buried behind a window, so it might not have moved. Excuse me. So I don't want kilograms. I want to turn that into pounds. And then I'll go look up the conversion from kilograms to pounds later. All right, so that one's done. To get from meters to miles, I needed to first turn meters, so that they cancel out, into kilometers, which I'll then turn into miles. And yeah, if you have a conversion from meters to miles, you could just go directly. So that one's done, and that one's done. And then finally, to get seconds squared into minutes squared, I need to... And I gotta do this down here, unfortunately. I need to cancel out these seconds on the bottom, so I gotta put them on the top. And I'm gonna do it this way. And then I'll turn them into minutes. So my second squared will cancel out with my second squared here. And now that I have the units that I want, which are pounds, miles per minute squared, we can do the numbers. And so that would be, how many kilograms are in how many pounds? So 1 kilogram is 2.204 pounds, I believe. I should probably look that up. I haven't used that number for a while. 1 kilogram, 2 pounds. 2.2046, yeah. So it's actually 2.205. How many meters are in a kilometer? That is 1,000. And then a mile is 1.609 kilometers. Let me double check that one. Yep. And then there are 60 seconds in a minute, but we're going to have to square that. We don't want to forget that squared. And that applies to everything in the parentheses. So that when I go to the calculator and I put all these numbers in, I will type in 1,800 times 2.205 times 60 squared divided by 1,000 times 1.609. And I get 8880.29, whatever these units are. I gave only 2 sig figs at the start, so I got to round it to 2 sig figs. There you go. That's about as messy as my dimensional analysis can get. I don't think any problem that I give you on the final is going to be that difficult. What else do we have? Any other questions? I have a cat that is apparently playing in the laundry closet because I hear it thumping over there. What are you doing over there? Yeah, so for those types of problems, you actually have to do each unit individually. Mostly because we don't have conversions that have 2 or 3 units in them. Later on in like 161 and 162, we'll start introducing constants that have a lot more units in them. Like, we haven't really dealt with constants in this class. Like, we've done Avogadro's number. And that's a constant, but we haven't had, like, the ideal gas constant, which has 4 units in it. And then we have a discussion about how the only purpose of constants is to make the units cancel out and to put a number. We'll do a little bit of that in 161. But yeah, that's how you do those problems. Just one step at a time. Anything else? Let me know. Random Lewis structures. Sure. Do you want me to do the ones on the worksheet, or do you want me to just grab a workbook? Let me get rid of this and open up. Wow, I have a lot of folders open. Oh, you know, I don't actually want the key for that one because it just shows you the answer. We'll get to the answer. We can't do inches to kilograms because those are not compatible units. So, like, inches are a length, but kilograms are a mass, so you can't convert one to another. That is not something that is doable. Let's see here. That will probably work. I just gotta make this bigger so I can read it. Alright, so whenever we do Lewis structures, you gotta remember the 5-step plan, right? What was the 5-step plan? The first step was counting all the valence electrons, so that's where we're always going to start whenever we draw a Lewis structure. The second step is to do your framework and connect all of your atoms together using electrons from the pool of electrons that you counted in step 1. In fact, I feel this strange sense of deja vu that I wrote all of this yesterday. So I'm going to pick, let's do carbonate. Let's do carbonate because that's an exciting one. We're going to apply that to all of the rules. So we're going to start by counting valence electrons. So grab your periodic table. And carbon has 4 valence electrons. Oxygen has 6 valence electrons, and there are 3 of them. And then this thing right here, to make something negatively charged, you have to give it extra electrons. 2 extra electrons. So if I were to add all these together, I get 18, 22, 24. So that tells me that I have 24 electrons to play with for this Lewis structure. All right. So that's step 1 done. Step 2, we're going to draw the framework. The central atom is always listed first. You just put it on the center. You put the other stuff around it. And then you connect it. Boop, boop, boop. So that used 2, 4, 6. 6 electrons. So now I have 18 left. That's my framework. For number 3, we got to do outer octets first. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, that used up all of my electrons. Now I got nothing left. So there's my outer octets. I don't have any electrons left to do inner octets. So we're just going to check that off as done. We're going to go straight to multiple bonds, where I have to take 2 of my electrons and go whoop, whoop. And that gives my octet to carbon. So what you see on the screen here, this would be the Lewis structure for carbonate. Now, something that we didn't really mention because we didn't do this, but whenever you have a Lewis structure for an ion, just put brackets around it and put its charge in the corner, like that. And there you go. So that's the first one. Let's do one more. Let's do C2H4. So we'll just go over here. We can do this over in the space. So step 1, count your electrons. Step 2, draw a framework. When there are multiple central atoms, generally what you want to do is just connect them together and then put everything around it as equally as possible. So this would probably be the right way to do this Lewis structure, by starting with this connection and then doing this. It's not common that you have unsymmetrical things, like 3 H's on one side and then 1 on the other. And you'd find out that if you tried to make the octet rule work that way, it wouldn't. So there's my framework. I used up 2, 4, 6, 8, 10 electrons, so now I have 2 electrons. There are no outer octets because they're all hydrogens, so I just have to put them on something in the middle for my inner octet. But this guy over here doesn't have his octet, so we're going to take those electrons and share them. And that's the correct structure. Some of these I gave you hints. Mostly because as Lewis structures get more complicated, there's not really a good way to figure out what the central atom is. This is just a model that I give you in Chem 140 and also in Chem 161 for simpler molecules. But once you get the gist of this and you go to organic chemistry, you start drawing just all these crazy structures like all over the place. So this won't be the last you see of Lewis structures. We do a lot of Lewis structures in 161. A lot of them. In fact, most of the ones we draw break the octet rule because the octet rule is not the end-all, be-all to drawing structures. But for our purposes, it's good enough. What else do we have here? Atomic mass from Unit 7. Let me find Unit 7. This one I can post the answers to. Let me put this over here so I can see it. That's probably a good one to do. So this is bromine. Here's all the information for bromine that you would need. I'm going to put this on the screen there so I can see it. I need more space. Hold on. Canvas size, link, percent, 500. And I gotta do this again. Was it F7? Yeah. Yeah. Paint. New layer. Close. CH3CN, I can just draw the structure really quickly, what that should be. So there's 4 single bonds, because there's that, and then there's this triple bond, and like that. So you should only have 1 pair of octets, and the reason for that is if you had the number of electrons that you showed, you'd have 2 too many, it looks like. That's the Lewis structure for CH3CN. whenever we give you a formula that looks kind of like that, a lot of times what the formula is written to do tries to tell you how the things are grouped together. But for the most part, a lot of this is just intuition, and you'll gain this as you do more examples. So, like, CH3 is a really common group. So is CN. CN is a really common group. What's not a really common group would be something like NH3. So, NH3 is ammonia. It floats around by itself. You won't actually see it on a molecule, but you would instead see it as NH2. Um, but again, those are things that you pick up as you do more of these. You'd be like, oh, I've seen that before, so I know what it looks like. Um, so as you gain that experience and also just do more examples of these types of problems, you'll intuitively just know how to draw these. So like you could tell me any structure and I would just be like, okay, do do. I don't know, like I could do something like that and just be like, okay, there's the structure. Just because I've done this for so long. And that's the sort of thing that you will develop as you progress. So let's do number 5 here. 5 should be in the viewfinder. I can actually tell. Yeah, it is. Okay. All right. So the atomic mass of bromine is 79.904. There's 2 isotopes, bromine 79 and bromine 81. What's the percent abundance of each? So remember that the formula for isotopic mass is... So the average mass is going to be equal to the percent abundance of isotope 1 times the mass of isotope 1 plus percent abundance of isotope 2 times the mass of isotope 2. Now I'm going to actually rename these 1s and 2s here. I'm going to rename this 79 and 81. And then what I'm going to do is I'm going to say, well, wait a second, I have 2 unknowns in my equation. These 2, because this is just a number I gave you, this is a number I gave you, and this is a number off the periodic table. If you have 2 unknowns, you need 2 equations to be able to solve for it, so you can substitute. And the second equation that you need is that the total percent of both of these has to equal 100%, which we're going to write as a decimal. All right, so now we just got to solve for one of them. And so I'm going to solve for 79. And then what I'm going to do is I'm going to make a substitution here. I'm going to call this guy Y. I'm going to call this guy X. So now what my formula is going to become, so this just went like that. I'm going to substitute the bottom expression here into the top. So I have M average equals percent 79, which we called Y, times M79. And then percent 81, which we called X, mass 81. Now, because this thing down here says Y equals something, I'm going to take that Y equals and just put it in here for Y. I'm going to stop with the green and black ink here. So that times percent 79 plus X times percent, or times... Oh, no, I'm sorry. Hold on. Like, there shouldn't be any percents in there, here anymore. I've already a substitute. So now that we're at that point, we'll just factor stuff out. So we got to multiply both of these by M79. So M79 times 1 is M79 minus x times M79 plus x times M81. Now what I'm going to do is I'm going to move this guy over here. And I'm going to switch these two terms. So I have the minus on the right. This is just to make it neater. So M average minus M79. And I'm doing that to get all the stuff that doesn't have X on the left, leaving only the stuff that has X on the right. Now I can factor out X here because both terms have an X in it. And that's going to equal this. And then I can solve for X by just dividing this part. Now, I know a lot of people are going to be like, can't I just plug in the numbers? I want to just plug in the numbers. Don't do it. Do the damn algebra first. And the reason you want to do the damn algebra is because you don't want to write all those numbers down 75 billion times. Look how many times I had to write this equation. Like, I do this 8 or 9 times. If one of the numbers you're entering is 78.9183 AMU over and over and over and over again, one of those times you're going to lose one of those digits or transpose one of those digits. You don't want to do that. Secondly, you don't want to deal with sig figs each time you combine two numbers together, because who knows how many times you did do that. When you get to the end, you can easily see, oh, I'm subtracting two numbers. Oh, I'm subtracting two numbers, and then I'm dividing those numbers. So the sig figs are much more trivial than they would be if you're doing this each step of the way. So do the algebra first. Always do the algebra first. Now we're going to substitute in the numbers. So what was the average mass? According to the periodic table, that was 79.904 AMU. That's the eraser. The mass of isotope 79 was 78.9183 AMU divided by mass of 81 was 80.9163 minus 78.9183. So when I do the subtraction, this number goes down to the thousandths place, but this goes down to the 10,000ths place. So this is actually the place that we're going to be rounding to. So I can punch this in my calculator and just round what it gives to the thousandths place. If you aren't sure if that will work for you, set it up vertically and just solve it. Better safe than sorry, right? So on the top here, I get 0.986 AMU. And then on the bottom, these both go to the 10,000ths place. So I'm going to round to that spot. And yeah, you're going to have a different number of sig figs for the top and the bottom. But that's okay, then you're doing division and it's easy to resolve. So 80.9163 minus 78.9183. And I get 1.9980. These AMU get canceled out because now I have something divided by itself. And so I can do 3 sig figs divided by 5 should be 3. So 0.986 over 1.9980. And I get 0.493, which is 49.3%. Now you're going to notice that, wait a second, how did you get that extra digit on there? And the answer is, if I had solved for x to be the other thing, So up here we made a choice here. Here's my x and here's my y. If I had switched which ones I was solving for and I solved for y instead, I actually get more sig figs. I get a different number of sig figs. It's weird. So don't worry too much that my answer has 4 and this answer that we just got has 3. Because we did it correctly, but the key is also correct. When you solve for the number that is larger, you tend to get more sig figs. And the reason for that is because of this issue here. If that number was just slightly bigger, 1 point something something something, I would end up with 4 sig figs, and my answer would have 4. So don't worry too much about the sig figs here. Just do the sig figs correctly for the iteration of the problem you choose. Now, if I know that x equals this, then I know that y must be 1 minus that, or this. And that should be what, percent 79? No, that's percent 81. There you go. So that's how you do that type of problem. So that's one with substitution. Without substitution is really easy, because you'll just be given an element that doesn't exist, and you have to find its atomic mass, and that's the only way to do it. Is you're going to just multiply percentages by masses and sum the results together. What else do we have on this list here? I think that's most of them, except for chemical equation where you have to find how much of one compound is produced when given only one mass. Can you give me an example, Alex? Like, what unit and then problem number from the worksheet? I think I know what you mean, but I want to be sure. How many times do we get for the final? You get 2 as always. Just in case, like, your computer crashes or something. I'm not going to suddenly be like, nope, you only get 1 try now. Like, that seems weird. Do I anticipate that you will need to take the final 2 times? No. If you have done well in exam 1 and 2, the final it's more or less the same. It's just I change the numbers around. Yeah, check for me and let me know so I can go over that. Can you go over question 12 on the Unit 12 worksheet? Sure. Let me find my worksheets. Let's see here. Oh, Adobe, stop opening all these options I don't need. Oh, that problem. Yeah, I chose that problem so that people would have to actually do a longer calculation. That's a really good problem. I like this one. This is also impossible for me to really put on Canvas because some of these problems are not programmable. Okay, there we go. All right, what mass of acetic acid has the same mass of carbon as 50 grams of baking soda? So, if you know how many grams of baking soda you have, you could feasibly turn that into moles of baking soda. And if you know how many moles of baking soda you have, you could figure out the moles of some component of it. I'm going to pick this component because that's what the problem's asking me. How much carbon is in there? Once you know that, amount, you could then instead do this. And say, okay, well, this amount of carbon in acetic acid would be moles of carbon, moles of acetic acid, grams of acetic acid. And then you might realize, well, wait a second, my carbon mass here is kind of a dead end. Do I really need to do that? No, you don't. You just go in this direction, right? Now, for reference, I gave you the mass of carbon. But in order to figure out this problem, I'm just going to start here and get here by doing it this way. So let's do that calculation. So we start with 50 grams of baking soda, which is... Oh, shoot, it's NaHCO3. Ha 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 ha. I was going to say, like, Na2CO3 is baking powder. Okay. We're going to turn grams into moles here. So grams to moles. By the way, for cooking purposes, just FYI. Just in case you see a recipe that calls for baking soda or baking powder, that's what you're putting in there. Moles of baking soda. We'll turn that into moles of carbon. And then we're going to turn moles of carbon. This is the same amount of carbon that's in the baking soda. We'll use that to figure out how much carbon is in the acetic acid. And then once we know how much acetic acid we have, we can figure out how many grams of acetic acid I have. So that shouldn't be too hard. Now I got to figure out what the mass of all these things is. So that's not Lentec. That's the wrong window. Oh, I don't even have Lentec open. I just grabbed a page that looked like... Let's see here. Calculator. I probably use Wolfram Alpha for this, but that's okay. So baking soda is 84.01 grams per mole. In sodium bicarbonate, there is 1 carbon. So 1 mole of NaHCO3 contains 1 mole of carbon. And then for acetic acid, I haven't actually written the formula for acetic acid here. But you can see that there are 2 carbon per 1 mole of acetic acid. Thought my cats were fighting. HC2H3O2. 60.05 is the mass. That's the eraser. Grams per mole. Times it all together, you should get what's on the screen. 50 times 1 times 1 times 1 times 60. That's not 60.05. There we go. Divided by 84.01 times 1 times 1 times 2. 17.87. Is that what we got? Yeah. Oops, I have too many sig figs, so my answer on there actually is wrong. Acetic acid. There we go. That's the correct number of sig figs. Oh, excuse me. Turn some number of formula units to grams. So you need to know what it is. We can make something up, though. That's not difficult to do. So if you had, I don't know, I use this a lot, so we'll just do that. So let's suppose that you have this many formula units of sodium phosphate, and you want to figure out what its mass is. So remember that formula units are just a method of counting, just like molecules or atoms or whatever. So I could turn this into moles, and then I could turn that into grams. We'll just call it fun. There you go. So there are some number of formula units in a mole, and then in a mole of Na3PO4, there will be some amount of grams of stuff. All right, how many anything are there in a mole? There are always Avogadro's number of things. And then in a mole of sodium phosphate, there are, I gotta look this up, Na3PO4, 163.94. And there you go. So we would type all this into the calculator. We should get a reasonable number, since times 10 to the 24 and times 10 to the 23 are dividing by each other. Times 163.94 over Avogadro. And I got 1,430 grams. That checks out. I picked a really big number. Boop, boop. Let's see here. Quiz 8. Determine the empirical formula of a compound that has these numbers. How many attempts do we get on the final? You get 2, like always. So how do we find an empirical formula? Empirical formulas are the ratios of of atoms to each other. So what we're going to do is we're going to figure out how many moles are in the sample, but we don't have a sample. We just have a percentage, right? Well, whenever you have a percentage, remember what you can do. You can assume the size of the sample. I'm going to assume it's 100 grams. Which means that in 100 grams, this many grams would be carbon, right? Yeah, the final's open all day. Alex, if you find a problem, let me know. And you can always email me if you Can't find it right now. I put this too close, so I'm going to just go whoop. All right, so now we turn grams of carbon into moles of carbon. That should be a decimal point. That didn't really look like one. Ah! I dropped my calculator because my eye itches or something. I don't know. I feel like I have something in the corner of my eye, like a hair or whatever. Which is always super frustrating. So you're going to do this a whole bunch. We're going to turn all of these moles, or all these grams into moles. 4.485 over 1.0079. And I get 4.4498. So that's actually... I don't know what that is. There we go. Oh no, I hear a sad cat. Meow. Meow. Where is the sad cat? Where is the sadness? Where are you? She was really loud and then not here at all, so I don't know. She's not sad, though. She just kind of sounds whiny. She gets all the hugs. Seriously, I probably hug her for like 20 minutes a day. Not all at once, but in like 4 or 5 separate intervals of, oh, the cat looks sad. Here, I'll hug her. All right, so now that we have all those moles there, we're going to take all these and make a formula. That's not the right formula. Hold on. C 4.995, H 4.450, O 2.220. And then we're going to divide by the smallest number, and we're going to see where that takes us. So 4.995 divided by 2.220 is 2.25. 4.450 divided by 2.220 is 2.0045. That's really close to 2. And then O is just divided by itself, so it's 1. Well, we're not allowed to have fractions here. This is a fraction, right? This is the same as 1 over 4. And to get rid of that fraction, I'm going to have to multiply everything by 4. So 2.25 times 4 should be 9. 2 times 4 is 8, and 1 times 4 is 4. There's your empirical formula. Oh, yeah, you definitely need a 1 at the end. Otherwise, you're going to be dividing by 2.2 over and over and over again. That'll definitely wreck your problem. Yeah. What's the difference between ounces and fluid ounces? Ounces are a weight, as in 16 ounces is a pound. And fluid ounces are a volume, as in 8 fluid ounces makes a cup. Honestly, the correct answer to that question, though, is they're imperial units, so fuck if I know or if anybody knows, right? Like, they're just stupid. Which is why we don't use them. We don't want to use imperial units. Let me get Alex's question before it scrolls off the screen here. Sorry, I'm trying to read top to bottom, and then I read bottom to top because I have the attention of a squirrel. So where am I? Okay, so 89.6 grams of CrCl3. So let me write out the reaction here. So I need more space, though. Actually, that'll probably be okay. So excess sodium hydroxide. So I'm going to guess that this is what happens. What am I missing here? I'm missing this. There we go. And then where's my numbers? There we go. 89.6. 89.6 grams of CrCl3 with excess NaOH, so I don't need to worry about that. How many grams of CrOH3 are produced? So this is your classic grams to moles to grams problem. So there we go. And then we'll do moles of that to moles of the product. And of course I run out of space because I don't know how to budget for space. Moles of this over, or grams of CrOH3. There we go. And now I got to go to Lentech a whole bunch. So let's see here. CrCl3, 158.36. This is 1 to 1 because there are 1s in the balanced chemical equation for those. And then Cr hydroxide, oops, 103.02. I hit the eraser. There we go. And so we'll punch all this in the calculator. 89.6 times 1 times 1 times 103.02 divided by 158.36. 58.3 grams chromium 3 hydroxide. There you go. That's the answer you should get for that. So if you have a fraction, you have to multiply that fraction by something to get the whole number. So yeah, back up on the problem up there. When I had the 2.25 in there, that's a fraction. Whenever you see those, you want to clear fractions by multiplying by a whole number. Because you can't have part of an atom in a formula, right? So if you had like C1.5H2O, that would not work. You can't have 1.5 carbons. Because what an empirical formula does is it's trying to give you the ratio of all the atoms, but the way that the math works out, the simplest ratio will always have a 1 with something, and then whatever else the other numbers happen to be. And so if your ratio is 1 to 1.5, that's actually in reality 2 to 3. But math can't do that. You can't divide something by itself and get 2 or another number. You're always going to have a 1 in there somewhere. So it's just sort of a consequence of how the math works out. Sometimes we have to do an extra step when you have a weird ratio. Why do you get an hour and 30 minutes for a 35 question final that some of us don't even finish, but we only get 2 hours for a 71 question final? Because most of you finish it in the time allotted. That's the short reason. If you want me to, I can give you the average time of what students took on the final. But I suspect if you are one of the students that is concerned about finishing it, you aren't going to like what you hear. But I'll do it anyway, so let's see here. Exam 2. Report. I have not actually gotten all of the scores out yet. I need to work on that. Average elapsed time, 70 minutes. So most students on average had 20 minutes to spare. That's just for one class. Let me get more data. Report, analysis. Yeah, same thing, 70 minutes. So when I write these exams, I have to put a time constraint on there because I don't want to assess scores in an environment where there is infinite time. So the time constraint is actually part of the design. The best way to improve how quickly you do these problems is do as many problems as you can. Now, how much time you will need to do those problems varies depending on person to person. So some people do like 2 or 3 problems and then they're like, sweet, I got it. I know what to do. And then they can do it forever. Some people need to do these like 10 or 15 times before they start to finally get into a routine. I don't know where an individual student falls on that scale, but the key thing that everybody has in common is you got to do as many problems as you can until you feel comfortable you get to that point. Where am I on the list here? I don't know where I'm at. Are these questions? Let's see. How do we determine the molecular formula assuming a given molar mass of a compound? Gabe, can you be more specific? I think what Kyle is telling you is the right strategy. But from the problem that you are telling me, I'm not certain that I have told you the correct information. Unit 4, question 4, worksheet. I can answer this question down here. The average is not out of 83, it's out of 75. Remember that there are extra credit questions. So 59 out of 59.3 out of 75 is actually a B. That's actually an average that's too high, in my opinion. So I could curve the scores down if you'd like me to be more fair and make sure that we have an equal distribution. But again, I suspect that you don't want me to do that. I think an average of 60 out of 75 is perfectly fine. Where am I? Worksheet. Folder. I need a folder. Oh, this is that combo one. That's why. That's the wrong thing. I want the key. There we go. And then this can go away. Yeah, the final is also extra credit, so it's out of 165. Same as all the exams. This isn't my first rodeo, you guys. I know it sounds like a lot of points, but I do this for a reason. If you are really, really good at all of this stuff, then these exams are no problem for you. I have people who are getting like 99% on these exams. So they're getting, I'm just raining extra credit points on them. And I need to have a way to differentiate those people from everybody else. There we go. Let me make sure that that fits on the screen there. That doesn't fit on the screen. Hold on. Okay. So where am I? An unknown liquid with volume da 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 has a mass of da 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 da. Is the liquid ethanol, hexane, or dichloromethane, or something else? All right. So this is just unit conversion hell. The reason that I have so many of these on the worksheet is because Samhita loves them. Samhita loves to give you, like, a swimming pool has dimensions 7,480 inches by 0.0086 kilometers by 13 and a half rods or whatever. What's the density of the water in there if the mass is something? She gives you all these ridiculous units, and so I basically have copied a lot of her problems and changed them around. So you get bullshit like this. Like, you're never gonna have to do this. Not in real life, but the whole point is to get these units into, that's a volume, so we're gonna need to turn that into milliliters. And we need to do that. So what I would do for this type of problem is I would go straight to Google and I would ask it how many grams per ounce. So 1 ounce equals grams. And it says 28.349 grams. So 1 ounce equals 28 point. I've already forgotten those numbers. 28.3495. So I'll just, whatever, we'll write it all down. And then 1 cup. How many milliliters is that? That I should know because I have it on a magnet on my fridge. And I actually use it often. 236.5. Okay, maybe I didn't know that. 236.588. So now, if I want to get density, I got to put grams on the top and milliliters on the bottom. So what I'm going to do is I'm going to do this. I have a 1.66 ounce sample with volume 0.25 to 1 cups. That would be a density, mass over volume. But those units aren't anything that we really want, so we're going to convert them. So I'm going to turn ounces into grams by doing that. And then I'm going to turn cups into milliliters by doing that. Now I'll have an answer that's in grams per milliliter. And so now I got to just punch in all the numbers. So in 1 cup, there are this many milliliters. And in 1 ounce, there are this many grams. All right. And when I punch all those numbers in my calculator, I get 0.789. And then the last part of the question is, well, what is it? Okay, well, I got a number in grams per milliliter. Which of these has the same density? Is it ethanol, hexane, or dichloromethane? Well, obviously it's ethanol because it's the same number, right? Also, who would pour hexane or dichloromethane into a cooking cup? That's sort of a meta thinking that you should not apply to these problems. Like, it could very well have been any of the other ones. I just picked a random chemical and then went and looked for 2 other ones that were common enough in the laboratory. So don't try and game the problem by looking at it and saying, well, you wouldn't really put dichloromethane in a measuring cup. Well, of course you wouldn't, but for the purposes of a chemistry problem, I'm just using containers. I think I'm all caught up. Oh, no, I missed your question, Chris, here. If you got C 1.5, H 2.50, you would times everything by 2. Yeah, so you get 3, 5, and 2. Because that ratio, that's an empirical formula. There's no number I can divide out of that to get whole numbers. If you have atoms and you're turning into moles, you want to divide by Avogadro's number. If you got that number times 10 to the 45, that looks like you multiplied. So if you had this many atoms and you wanted to turn that into moles, remember that in 1 mole there are always Avogadro's number of atoms. Oh, if you divided, then this is what happened. So if you punch in your calculator this, so there's the first number, divided by this, what your calculator does is it says, okay, I'm going to take these numbers and multiply them together. Okay, I'm going to take that result and divide by this. Okay, I'm going to take that result and multiply by that, which is not what you want, right? That's an issue. So what you need to do to fix that is to do this. Because now what your calculator does is it says, oh, you want me to divide by that whole thing, not just 6.022. Because calculators are dumb, remember. So if you are punching in all of the commands one by one and hitting enter, that is almost assuredly the issue. Always put parentheses around the bottom term, especially when using Avogadro's number, because it has a times in there. I mean, it's better to find that out now than to not find it out at all. Wow, I don't know what everybody's so loud about out there. My other cat came by and is like, meow, 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 meow. IBR is iodine monobromide. That's right. Hold on a second. Stop that! I have no idea what he's yelling at. Yeah, be careful when using your calculator, because it has no idea what you intend for it to do. It just follows a pre-programmed set of directions that we call order of operations. There's a really popular, like, dumb thing that goes around on the internet all the time. So, like something like this, right? This meme that shows up all the time. And everybody goes, oh, okay, well, I do this part first, and then I multiply these two together, and then I divide, right? And the answer is no, that's not what you do. Is you follow order of operations, so this does become 4, but then this expression becomes this, and you do it left to right. So 6 divided by 2 is 3, times 4 is 12. And this is basically that calculator issue you're running into, is if you punch this in your calculator, it will spit out 12, but you are probably expecting it to spit out whatever 6 divided by 8 is, 0.75. What was the name of the website I was going to for mole-to-mole conversions? Let me get that out for you here. So there's two. I prefer this one because this is all it does. This is Lentech. You could also use Wolfram Alpha. That one you could just look up. Wolfram Alpha is a really good calculator. If you do not have a scientific calculator for this class, use Wolfram Alpha. It'll do all the calculations for you. Yeah, don't calculate molar masses. Like, don't waste time. This is an online class. I'm not going to say, no, you must use a periodic table to add those numbers together. Like, don't be silly. If you were doing this for, like, homework or outside work or for anyone else as, like, a profession, you would look up these numbers on Lentech. Like, it's basically the same argument as, oh, you should be doing all of your algebra by hand and all of your addition and subtraction on paper. Like, no, we know how to add and subtract. You punch in a calculator. That said, there is merit to not using a calculator because it makes you better at math. Like, I've taken calculus classes where I wasn't allowed to use a calculator, and I was like, this is fine. I know what sine of pi is. It's 0, so I could do that sort of thing. Yeah, for that problem that you have there, turn everything into moles and then do the... is that an empirical formula? That looks like an empirical formula. Turn everything into moles and then you can make the formula. Yeah. So 20.35 grams of carbon would be like... that's probably like 1.5 moles or so. Maybe 1.75, something like that. 2.540 moles of H is just that. That many atoms of oxygen is like... a little more than 1.5. Yeah, 1.6 something. There you go. And then you just make a ratio out of all of them. The link is not showing up in the chat box. So I can see it on the screen here, but I also don't know what you see. I am the moderator, so I should be able to... I don't want to do that. Let's do it this way. So type Lentech molar mass into Google. So we'll just write that. It's probably trying to squelch my links. I don't really know why. Yeah, I have no doubt that it's letting me type in the chat. Like, I could just la 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 la, I can do whatever. But I don't know if live chat likes links or not. You can see the link on the screen, at least. That's why I saved the chat log. But if you type in Lentech molar mass, it should be the first thing that pops up. If not, like, I have trained Google to do that for me. Like, in the search results. So single elements with non-bonding pairs and stuff. So my best guess as to what that problem would be like would be, okay, well, if I drew boron has 3 valence electrons, so I draw that. And so this would have 3 unpaired and 0 paired. That's my best guess. If you go to the Lentech homepage instead, then the formula, because I was just there, actually. So you want to go to calculators, and then molecular weight calculator. I can type that in the chat, too. So Lentech calculators, molecular weight calculator. There you go. They actually have a lot of calculators on here that I've never used any of these other ones, but Like, I don't understand why they have all these calculators, because they're a water treatment facility. So, like, my best guess is that they, like, do chlorine everywhere. For carbon, carbon has 4 valence electrons. And so it'd look like this. And so they'd all be unpaired. Oh, oxygen, yeah. Oxygen would be 1, 2, 3, 4, 5, 6. So you have 2 unpaired. And depending on what the problem is asking you, you could either say 2 pairs or 4 paired electrons. Really, what I'm trying to get you to do is count the number of dots that are in what situation, and then report that. And the reason for that is because I don't have a way to, like, I can't make you draw a Lewis structure. So read the question carefully. It may ask you for pairs, or it may ask you for paired electrons. And I have programmed it to accept whatever the appropriate answer is. Now that I think about it, I remember having that thought exactly when I was writing that question. And I was like, oh, I need to be specific here. What else do we have? Anything else? They must, like, a lot of these calculators, I could use, and a lot of them I only like, what is this? Energy to heat water. So, like, we do that in 162. We do that sort of calculation. Kinematic viscosity, though, like, that's engineering to something. Like, that's dynamics. Like, so there's osmotic pressure. So I do that. I do that in bio in Chem 121. But a lot of these, I'm just like, holy crap! Like, how many pies do they have their fingers in? It's really cool. I should probably just click around on all of these. Like, there's a hardness converter, and I'm like, is that like Mohs hardness? Oh, it's water hardness. Yeah, that makes sense. Okay. How much calcium and how much magnesium are in the water? Yeah, that checks out. Here I am thinking about a geologist, and instead they're like, no, we meant water hardness. Duh, we're a water treatment plant. If I have this many moles of acetic acid and I need to get H atoms, would I convert the moles of H and then get atoms? Yes, that's correct. So you turn moles of acetic acid into moles of H, and then moles of H into atoms of H. Question 7 on Unit 12. Do I have Unit 12 open? I do. Hey, that's one of my exam questions that I always put on my in-class exams. Yeah, what is the mass of one atom? How the hell are you supposed to calculate that? Like, how do you figure out what one atom weighs? Well, actually, it's really trivial. How do you figure out how much any sample of atoms weighs? Well, you turn atoms into moles, and then you turn moles into grams, right? It's just that when I do this type of analysis, we're only working with one atom, and so everybody looks at that and goes, wow, that's weird. So they freak out. But if I gave you like 10 to the 20 atoms, you would easily be able to do this problem. So in a mole, there are Avogadro's number. So that'd be how many moles we have. And then I got to multiply by the molar mass of phosphorus, which I don't have. 30.974. And this should give you the number on the screen. There you go. And I could do that with any atom I wanted. Usually I do thorium. Because hooray Thor, that sort of thing, right? Thorium is named after the god of thunder. In fact, many atoms are named after deities. Like Helios is what? The sun deity? That's where helium comes from. And the reason for that is because the first detection of helium was in the sun. They did spectroscopy and are like, hey, wait a second, what is this gas? Oh, we're going to call it helium. Wait, we have this on Earth. We could put balloons in it. Or we could put in balloons. And then throw parties. And so they did. They threw a party. Don't buy helium and put in balloons, by the way. It's such a waste. We need our helium for MRI and medical imaging. All right, we got like 10 more minutes, so let me do last call for questions here. I'm not going to put the title screen up and put the music on. Like, that'd be silly for like 5 more minutes of questions. So I'm just going to ask if anybody has any last questions they want me to go over. Gotta pour more of my seltzer water into my glass here. I'm now addicted to seltzer water. It's great. It's really great. I was gonna say it's kind of sad, but no, it's really great. It's how you know you're getting old. Is when things like seltzer water appeal to you. We actually did that question, I believe. Or we did one similar to it. I gotta find it. There it is, right there on the screen. So this was how much CrOH3 is made. But you could do the same exact process for how much NaOH would be reacted with it by just changing out what you're solving for. So rewind the video and you can see that one. What else do we got? We don't need this. This is just calculator memes and stuff. Worksheet 16. Which one? 13A? I'm trying to make it fit in here. I gotta make this bigger. All right, let's see if we can try that. So what volume of 0.6250 molar NaOH will react with that many grams of phosphoric acid? So what we would do is we would say grams of phosphoric acid turns into moles, turns into moles of whatever this is that we're reacting, NaOH, and into a volume. What am I doing here? Grams. There we go. So we'll do grams into moles. And then we'll do moles into moles of sodium hydroxide. And then we'll do a volume. So moles of sodium hydroxide into liters. So these cancel, and these cancel, and these cancel. What is phosphoric acid? Where's my Lentech? Oh, that's the water hardness calculator that I was playing with. That's another way that you know that you're getting old. You find random calculators on a water treatment website and just start entering numbers in them and going like, oh, that's neat. Like, who does that when they're 10, right? Or 16 or what have you. If you did, then congratulations on your curiosity, I guess. I don't know. 98 grams per mole. This equation is balanced, so I need 3 sodium hydroxide per 1 phosphoric acid. And then the molarity of this is 0.6250 moles per liter. We'll punch it all in the calculator. 71.62 times 3 divided by 98 times 0.6250. I have 3.507 9 liters. So actually 3.508. Which is the answer that is shown on the screen. So that is how you do that one. Can I get B on the screen without having to reformat this window? Yeah, there we go. And then what volume of this will react with this? So this is a... Uh-oh. Hold on. We gotta do this again. Anchor... Make it twice as big. There we go. F7. Background. That's not white. There we go. Boop. New layer. Oh, I ruined everything. Hold on. I didn't ruin everything. I just lost the green color I was working with, so that's close enough. Okay. So this is a volume and molarity are given problem. How do I figure out the volume of the other one? You can do... Oops, I don't need to do that. I'll just erase that. You could do volume of something to moles by using the molarity, right? Because volume times molarity equals moles. So volume of the starting thing, which would be NaOH, because I know both numbers. And then I could turn moles of sodium hydroxide into moles of phosphoric acid. And I could turn that into a volume of phosphoric acid using the molarity. So I need to turn volume into liters, so we're going to just do that automatically. So molarity times volume would be these two multiplied together. Make sure you're multiplying the correct molarity, because the problem does give you two of them. So that would be moles. Now I can go moles of sodium hydroxide to moles of phosphoric acid. And then, well, I'll put that number in later. And then finally, moles H3PO4, volume H3PO4, oops, which would be liters. So this is still 3-to-1, based on the balanced chemical equation from before. And then the molarity of this acid is 0.1715 moles per liter. And so you should get 0.025 times 0.4415 divided by 3 times 0.1715. 21.45? Yep, that's what we got. When you use the MSVS stuff, remember so what was the name of that formula? Remember that this is the dilution formula. Which means that you use it for dilutions only. Is this a dilution? No, because you're doing a reaction, right? Reactions and dilutions are not the same thing. So don't use on chemical reactions. So since we did chemistry, we have things that are reacting with each other. Do not use the dilution formula. Dilutions are not reactions. Yeah, well, so reaction is a keyword, but it's more important to understand the context of what you're doing in the problem. So like in this problem, we're trying to do chemistry. But in a dilution problem, you're going to be mixing things by adding water to them, which is not a reaction. So you might not see the word reaction in the problems, but you should be able to know when a reaction is happening. So like I might say phosphoric acid and sodium hydroxide are mixed together. The resulting mass of product is da 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 da. But I didn't say the word reaction. But you could still tell from the gist of the problem that, hey, this is not a dilution. We're doing chemistry in this problem. So make sure that you are understanding what the problem is actually asking you to do. I want to say that almost every problem I've ever seen with a dilution actually uses the word dilute in it, because that's a pretty specific verb. Like, a laboratory procedure requires the preparation of this molarity. You have this thing. How would you perform the dilution? There you go. I guess I could just not say that last sentence. I could just be more vague about it and say, what do you do? But yeah, make sure you are looking at the problem with a critical eye and trying to find words that help you pick out what the problem is asking you to do. And I have to make it clear for you. Like, obviously I can't obscure all the words. As much as I want to try to like hide what's going on in the problem, if I read the problem and I can't understand what's going on, it's not a good problem. So there has to be language in there that tells you. Yeah, no problem. Let me know if there's anything else I could do. Last call for any questions before we call it a night. Almost done with the quarter. All you do is take the final tomorrow. Then you can play Cyberpunk 2077 all you want. Get all the seizures. Seriously, like, be careful. People are getting seizures playing that game. I'm very excited to play it in like 1 or 2 years when I build another computer that'll actually run it. I could probably play it on the minimum settings, like absolute bare minimum, but why? Hooray! What are my plans for the rest of the evening so that you can get a hold of me if you have questions? So, I'm still grading Lab 4. I'm like halfway done. I did half of them yesterday. And then I had to go to the store. If I didn't buy groceries yesterday, I was basically going to be eating rice and bread. I needed other things. So, I didn't finish those yesterday, and then it got late and I got tired. The first thing I'm going to do after this recording goes onto YouTube is that I'm going to immediately go to the exam 2 scores and process them. Like the discussion we had earlier. So it says they're out of 83, but remember they're out of 75 because of extra credit. So I have to change what Canvas thinks the scores are and then re-upload them. So I'll get your exam 2 scores up. Then I am going to finish working on lab number 4, get all of those done. I will post all those scores tonight and send out all those files. Anything NQA related, please get it to me by Friday, as well as your lab number 5. If you haven't finished that, just try and get it up as soon as you can so that I have it. On Friday, I'm going to download everything and do all of that and all the NQA stuff. I don't know if I'm going to be able to get those labs back to you. I might just upload your scores because there will not be any like remarks on them other than a score. So I don't know if that's really worth your time downloading those. Anything NQA that is sent to me, I probably also won't get back to you because I'm going to be in a hurry just trying to get everything done. Because grades are due a lot quicker than I wish they would be. And then you're done. You're done with 140. Forever. Hooray. Alright, so I'm going to end the stream here so that this can start processing. Make sure you've completed all your studying and preparation by midnight tonight, because the final exam opens at midnight. You can take the exam at midnight if you want. Almost nobody does that. I want to thank everybody for a great quarter and for working very hard. I realize that during a pandemic is not the easiest time to take a class. But I really do appreciate all the effort that everybody's putting into making these streams successful. And I wish you all the very best of luck and success on the final, all the rest of your classes, and I'll see you in Chem 161. Have a good one.